Well, my aim in this initial talk is really just to skim over a lot of topics, starting from one or two which are purely historical, and then moving into the nature of constants of physics and to aspects of cosmology, highlighting things you're going to hear about in the talks to come from other speakers who are more specialized around particular topics. Well, let's just start with a few reminiscences about when people started to become interested in the status of constants of physics in a way that was not purely in order to count the number of bags of jute that were coming into Dundee in the 19th century, or to find units for counting apples and oranges and other things in the 19th century. When the Industrial Revolution meant that there really was an explosion in the need for units to talk about all sorts of types of freight and goods. And a rather great Irish physicist called George Johnson Stoney was tasked with the job of somehow coordinating all these great systems of imperial and semi-imperial units that the British Empire had spawned. And at the British Association meeting in Belfast in 1881, Stoney was charged with chairing a committee to investigate this, but he did something completely unexpected and really just took over the committee and made his own report and told them what was the interesting thing to say. You see, Stoney was the person who had predicted the existence of what we now call the electron, and he had named it, and he predicted the numerical value of its electric charge. Somehow Thomson gets the credit entirely for the experimental discovery. But Johnson Stoney was able to predict the charge using Avogadro's number and Faraday's law. And so he was greatly sort of taken with the concept of a fundamental charge. And the value of that charge he called E, as we do today. And what he argued on behalf of his committee was that for all these units that there were spinning around, there were three types of unit of mass, length and time that were much more fundamental and deeper than all these other utilitarian applications. And he argued that one of the benefits of his electron charge was that you could combine it with Newton's constant and with the speed of light, this is pre-relativity, to make fundamental units of mass, length and time, which were not dependent upon any human constructions. And of course, if you're in a space with n dimensions, there is a dimensionless combination of these quantities and Planck's constant, which in 3 dimensions is just E squared over hc, related to the fine structure constant. And so if you wish, in each of these formulae, you could replace E squared by hc or h bar c, and you would have what about 18 years later Planck proposed as his so-called Planck units. They're essentially the same thing as Johnson-Stoney's units. So Planck, really like Stoney, was interested in setting up units of mass, length and time that were as separated conceptually as possible from any type of human construction. So he wanted to pick on things that were defined by the gravitational, quantum and relativistic characteristics of the universe. And there are still interesting things that you can learn from dimensional analysis of these sorts of quantity. You could combine G, H and C to make quantities with the dimension of pretty much anything you wanted in physics, force, moment of inertia and so forth. If you add Boltzmann's constant, you could create a temperature. And one of the interesting things you find, if you create a Planck unit of force, it's c to the 4th over 4g, and if you had a Planck unit of power, you just multiply it by c. But those Planck units don't contain h, so they're purely classical. And in fact, it's a reasonable conjecture that many people have explored and attempted to prove that there is a maximum force in general relativity, and it's given by this value here. And I think Gary Gibbons calls it maximum tension. And there is also a maximum power that can be arrived at in a gravitating classical system, and it's given by c to the 5th times 4g. Well, Einstein himself was greatly interested in the nature of constants, both in cosmology and in the rest of physics. And he wrote very extensively on this topic, although not in the open literature. Almost all of his writings on this topic are contained in a lifelong correspondence with Ilse Rosenthal Schneider, who was a student friend of his, who eventually married a philosopher of science and went to live in Sydney, and died not many years ago now, I think aged 102. And you'll find there's an article by Rosenthal Schneider in the Library of Living Philosophers volumes dedicated to Einstein, and it's on this topic. So she probed Einstein in her letters about the idea and status of constants. And Einstein thought carefully and wrote carefully in reply, and he tried to classify for her what he called geometrical constants, so things like 2 pi, and things that were just conversion factors between different quantities with different units. So this would be a quantity like the Boltzmann constant, just a conversion factor between energy and temperature. And then what he called real constants, so-called dimensionless parameters, like the fine structure constant or the electron-proton mass. And these, he hoped, might ultimately be reducible to quantities of this sort. And then finally, he allowed for the possibility that there must be some cosmological parameters. Certainly, he believed the curvature of space. He was rather reluctant to invest again in thinking about the cosmological constant, but more about that later. So what Einstein was really greatly preoccupied by in this correspondence and in other published papers was whether these dimensionless constants, which seemingly could have different values in the equations that we now had, were really freely changeable. So were they specified by some unique theory of everything, which is what he believed. So the issue, sort of rather geometrically, is that are the constants of physics rigid, rather like a triangle of rods here? Or are they not rigid, rather like a quadrilateral or a square, which can be very slightly distorted into a parallelogram, but remain structurally coherent? Well, on the dimensionless constants, the geometrical ones rather, there are one or two interesting things to say. Einstein published a paper in 1911 where he posed as a problem, which he didn't solve, he regarded as a puzzle, why dimensional analysis was so effective in physics. So why the constants of order unity so often did turn out to be of order unity in ordinary everyday physical problems. So this is like asking why dimensional analysis, which determined that the period of a simple pendulum depends on the square root of its length divided by the acceleration due to gravity, gives such a very good answer, in that the constant of proportionality is 2 pi rather than 2 pi to the power 10, in which case it wouldn't be very useful. Well, the answer, I think, to this problem, which Einstein didn't arrive at, is that these dimensionless factors are small typically because we live in a world of rather small number of spatial dimensions. All these sorts of constants like 2 pi tend to derive from formulae for volumes and areas of spheres or circles. They're a reflection of implicit symmetry in the problem. If it's a statistical problem like three-dimensional Gaussian, then the symmetry is implicit in the three-dimensional problem by seeing that things just depend, say, on r squared rather than on 3 different dimensions. And the volume of an n-dimensional sphere with radius r, you can look up in your copy of Gradstein or whatever, and you get this rather worrying formula. And when n is 3, these constants of nature just become 4/3 pi. But if you let the number of dimensions become very, very large, this dimensionless factor becomes really huge. So it departs from order unity, either bigger or less than 1, at a rate of n to the n, as n grows very large. So if we could live in a world with a huge number of dimensions, which we probably couldn't for other reasons, we wouldn't find dimensional analysis a very useful tool. Well, Einstein's other interest, which predominates searches for fundamental explanations of the world, and attempts to understand which aspects of the nature of things are tied to forces of nature, are so-called dimensionless constants. The famous one introduced by Sommerfeld, that we'll hear more about this morning from John Webb, E squared over h bar c, the fine structure constant. These sorts of quantities are the ones that physicists mean today by dimensionless constants. They don't care what units you use to describe the quantities that make them up. They're pure numbers. And a world in which these pure numbers were different would be a very different world, and perhaps a world that we couldn't be in. There's always been a hope that was echoed in Einstein's comments that some theory of everything might ultimately, uniquely and completely explain the values of these constants. I think probably in the 1970s and early 80s, when I was a student and postdoc, this view was still rather prevalent. I think it will be hard to find anyone who might try to defend it today. So today people are much more open to the idea that various aspects of the constants of nature arise at random. The vacuum state of the universe is not necessarily unique, that there are many possible self-consistent realizations of the laws of physics which have different values of these parameters. And I think John Ellis is going to introduce us in a more serious way to this type of problem. In the standard model, for example, you can, of the strong electroweak interactions, you can do a count of the number of parameters that need to be fixed experimentally, and this tends to give you 18 or so, and you'll need some extra ones if you want to then introduce something beyond that model, like massive neutrinos. If you want to go and include supersymmetry, then perhaps in principle there could be a huge number, a very large number of extra constants. If you make typical simplifying assumptions that there are not lots of new sources of CP violation, for example, no flavor changing neutral currents, then you can reduce the number of extra constants that you need to just 19. As I'm sure John will say, there are other reasons for thinking that if you probe deeper, that you might find that your extension of supersymmetry gives you ways in which you can unify some of these constants here and actually reduce the number of free parameters in the standard model. Well, cosmology also has its own parameters and constants. We might call these constants of nature if we wish, or we might just call them pieces of initial data which define our cosmology and distinguish it from others that we might think of. And if you look at our famous analyses of the data from the Wilkinson WMAP satellite and more recently from Planck, both these teams start with a minimal cosmological model whose parameters they are trying to fit and demonstrate that they are self-consistent. And that model is usually called lambda CDM, so a cosmological constant plus a matter source of cold dark matter as well as baryons. And these models will have a 6-parameter fitting family, and if you wish you could pick on those parameters to be the Hubble rate, so the expansion rate of the universe today, the present density of baryons, the present density of dark matter, a measure of the optical depth at some reference wavelength, and then a measure of the inhomogeneity if one assumes that this power spectrum is a power law on large scales and small wave numbers, then your other 2 parameters are the amplitude and the spectral index of that power spectrum. So it's important to recognize that this is just the simplest scenario that you could think of, and it's interesting to compare it with what would be the general number of parameters that you would need to describe a cosmological solution of general relativity that contains a number of parameters. So if we're doing an initial value problem here, and here is some t is constant surface that we're evolving forwards in time from, then in vacuum, the Einstein equations in a synchronous reference system would require us to specify 6 spatial components of the symmetric metric and 6 time derivatives of those quantities. But we could kill off 4 of them by using the 4 Einstein constraint equations, and then we could use the 4 coordinate covariances of general relativity to remove 4 others. So in vacuum, we would be left with 4 functions of space specifying the initial conditions. This, incidentally, this type of count is the sort of thing that Einstein was trying to do, perhaps making rather heavy weather of, with his idea of the strength of a system of differential equations, which is what he wrote about in Meaning of Relativity, for example, as a way of trying to identify which types of unified theory were stronger or better defined with fewer parameters than others. If you add a perfect fluid, then each one of them requires 1 pressure-density relation, if you assume there's an equation of state, and 3 velocity, non-co-moving velocity components. If you add a scalar field, then you require 2 functions for each one of them, phi and phi dot. Phi is the field. So if you add this up, you can see that if you have a cosmological solution in general to Einstein's equations, and it contains F matter fields and S scalar fields, then you're going to require 4 times 1 plus F plus 2F spatial functions to specify the cosmological solution. If, as some of our speakers, I think Pedro Ferreira will talk about, if one moves to higher order gravity theories, modified gravity theories, as possible explanations of the dark energy, then you're dealing almost always with field equations which now become 4th order. And so you now require 6 extra G double dot and 6 G triple dot components, and the number of parameters required becomes 16 plus this 4F plus 2S. Well, our standard scenario, we certainly require 5. Baryons, cold dark matter, dark energy, let's assume that it's a field rather than just a constant, and photons and neutrinos. If you wanted to have several different varieties of neutrino and not assume they're all the same, then you would have 3 of those rather than 1. So you're looking at the simplest scenario with no scalar fields as having at least 24 functions that you need to specify in order to determine the geometry of the universe. If it's homogeneous, so everything is uniform, then they would just become constants. So what are all these extra constants? Well, of course, almost all of them are different types of anisotropy in the curvature and in the expansion rate, which are seemingly very, very small. But if you introduce them, you would be able to use these observations to constrain each one of them, either on our past light cone or on a slice of the universe at the time of last scattering. If you do unusual things with the spatial topology of the universe, in the case where it's spatially flat or open, as is fashionable sometimes, then the number of constants or number of parameters that you require to describe the universe increases very significantly. And it does in a very unusual way. The most special type of anisotropic universes of so-called Bianchi type 1 become almost the most general type of universe that you're allowed to have when the space is compactified. And instead of having, in the type 1 case, just 1 plus F constants to specify the cosmology, you require 10 plus F because of the 3 extra identification scales for the type topology and the angles and the time derivatives of all those quantities, less a new time translation and 1 constraint equation only for this geometry. Well, there's one quantity here which is sort of lurking in the background. I mentioned it as dark energy, and that's the cosmological constant that we'll hear 2 talks from Dr. Padmanabhan about later in the week. And this is the big problem in cosmology. Nobody quite knows what the status of this constant actually is relative to astronomical observations. So is the dark energy just a cosmological constant, or is it some slowly varying scalar field or some modification of gravity that mimics the behaviour of the cosmological constant at late times and on large scales? It's worth emphasising that the lambda problem, or the problem of explaining why the value of lambda is so small today and why it's non-zero perhaps as well, is different from the dark energy problem. If one solved the dark energy problem tomorrow by discovering that it was some very particular slowly varying scalar field that was predicted by a new sort of theory, we would still have the problem of explaining why the cosmological constant has a value which is far, far smaller than the observations would permit. High energy physics notoriously wants to try to give a value of the cosmological constant that's vastly bigger than the observed value of about 10 to the minus 121 in those Planck units I mentioned earlier. Why this is a nasty problem is that you might think that there would be some special initial condition which you could just presume with this very small value, worry about it later, it would eventually come to dominate the expansion of the universe. Unfortunately, if you set the initial value to be incredibly small in that way, each time the universe goes through a symmetry breaking transformation, symmetry breaking scale, it will reinstate the value of this constant at the energy scale of the symmetry breaking. And there are several of those breakings that occur at different epochs in the early universe that would just reinstate an unacceptably large value of the cosmological constant, despite you having set it to have an initially small value. There is also an interesting issue as to whether its value does actually have an explanation in the usual way. So most physicists would hope that there is some deep theory which can make a conventional type of testable prediction that this quantity has this value today. That is, for example, that it's the Planck time over the present age of the universe squared, for example. But it might be that there isn't such an explanation and that it just arises at random by some symmetry breaking process. And there's no further explanation of it other than that it's rather fortunate that it fell out with a value that happens to allow galaxies and stars and astronomers to subsequently come on the scene. Most particle physicists are rather aghast at this possibility because it makes them redundant perhaps in certain ways. But there's an interesting, I think, little historical parable that you could tell which makes you think twice about it. If you go back to 1600, when Kepler was in his prime and thinking about developing his new laws of mechanics for the solar system, if you had suggested to Kepler that the number of planets in the solar system is not fundamental, it's just something that happens at random, it's just a historical accident, Kepler would have found that idea completely anathema. For him, the number of planets in the solar system was deeply fundamental. It was bound up with Platonic and Pythagorean symmetries about the nature of the universe. So he was a type of string theorist of his day. But others, like Huygens, of course, said fairly vociferously, it's all complete nonsense. There's nothing fundamental about the number of planets at all. It's just an accident. And indeed, those critics were right. No planetary astrophysicist in their right mind today would try to predict how many planets there are in the solar system or in any other planetary system. They recognise this is one of the things that falls out by accident, like the number of green cars that happen to drive past in the next hour. There are other things which are fundamental, which can be predicted about planetary systems, but the number of planets in them doesn't happen to be one of them. And so it might be here. There is an anthropic upper bound that Dipper and I found long ago, and Weinberg subsequently wanted to transform into an actual prediction. An interesting comment about this is that if one applies the same logic, say, to the curvature of the universe, then there is also an anthropic bound. The curvature can't depart too greatly from flatness, but the observed bound on the curvature is well below the anthropic bound. What do insightful people have to say about the cosmological constant long ago? Lemaitre's comment in 1949 is rather interesting. He says to suppose that it's exactly zero would mean that the conventional level from which physicists use to count energy is more fundamental than any other they could have chosen just as well. So Lemaitre was the first person to interpret the cosmological constant as a vacuum energy density with a pressure equal to minus the density times the speed of light squared. So he has this rather deeper perspective on it as something that is associated with some sort of absolute zero of energy in the universe. Einstein's often reported as saying that introducing the cosmological constant was the greatest blunder of his life. I've never found any evidence that he made that comment, but I also know that he did make that comment about something else. He said that the greatest blunder he made was advising about the atomic bomb to Truman. But I did find a letter that he wrote to Lemaitre in 1947 where he writes at greater length. And he said he found the cosmological constant very ugly indeed, in that the field law of gravitation should be composed of two logically independent terms which are connected by addition. So the Force law is 1 over r squared plus a constant times r. About the justification of such feelings concerning logical simplicity, it's difficult to argue. I cannot help to feel it strongly that I'm unable to believe that such an ugly thing should be realized in nature. And if you could have persuaded him it was linked to quantum theory, that would have been the final nail in the coffin, I think. Well, what can we say about these sorts of constants of nature, cosmological and non-cosmological? Situations rather peculiar, almost paradoxical. The measurement of the values of constants of nature is where we find usually the greatest experimental accuracy anywhere in physics. And yet, with our understanding of the theoretical values that are measured, we find our greatest theoretical ignorance. So nobody has any idea really why any of those dimensionless constants have the precise numerical values that they do. And there are no predictions for future values. Theories of everything are rather peculiar in the direction that they've taken. In a direction like string theory, for example, there are many more dimensions of space seemingly required than the 3 that we walk around in. And so the true constants of nature are not even defined in our 3 dimensions. What we are seeing are some shadows of the truly fundamental constants that exist in 10 or 26 dimensions, and some dimensional reduction process that has arrived at 3 dimensions becoming large has also produced a connection between the values of the quantities we call constants in 3 dimensions and the truly fundamental higher dimensional constants. The last of these questions here that are posed, are they really constant, is something that we'll hear quite a lot about today and then later from John Webb. What's the motivation for that? Well, if one takes particle physics models seriously with extra dimensions, then any change in the value and the size of those extra dimensions will precipitate changes at the same rate in the 3-dimensional constants, or the shadows of the multi-dimensional constants that define the theory. If symmetry breaking occurs at particular epochs in the temperature history of the early universe, then there can be spatial variations in quantities that we go on to call constants of nature. This might be something like the matter-antimatter imbalance in the universe, or the magnitude of CP violation from place to place. The multiverse is something we'll probably hear about from different speakers, and certainly Martin Rees, I suspect, will have something to say about it in his public talk today. This scenario produces a profusion of possible universes with different defining parameters. And string theory teaches us that we shouldn't believe that the vacuum state is unique, and therefore you can have self-consistently defined scenarios for physics in which underlying constants determined by the vacuum energy state of the theory can be different. And cosmologically, some parts of the universe might roll into one vacuum state, some into another, and conceivably there might then be subsequent evolution from one state to the other, just as there is in the scenario of inflation. These sort of cartoons here of chaotic and internal inflation sort of give you the perspective on this scenario. The conventional inflationary picture has it that our entire visible universe is the expanded image of a tiny causally connected quantum fluctuation in the very early universe. There are, of course, many other fluctuating regions beyond the horizon of that initial patch, and if they inflate perhaps by different amounts, perhaps not at all, then beyond our horizon we will have regions of the universe which have very different observational characteristics, if only we could see them. What's interesting to stress about this scenario for philosophers is that there has always been a sort of overly positivistic caution that while we're making observations within our visible horizon and discovering various properties of the universe, there is no reason to assume that if we kept on going beyond our horizon, that things would remain fundamentally the same. But such a caution has always been rather negative. But I think the interesting feature of chaotic inflation in this sense is that for the first time you have a positive prediction that you should expect this to be the case. That globally the universe will be expected to be highly inhomogeneous and very complicated, making use of all those 24 plus arbitrary functions of space needed to specify it. But locally, most of those functions would be rather smooth and constant, or even zero, and it looks pretty much like an isotropic and homogeneous Friedmann model with a near Gaussian spectrum of fluctuations. The time development of this type of scenario, known as internal inflation, is the scheme. You recall that through quantum random walking of a scalar field which produces inflation, any region that inflates necessarily creates within itself subregions which are able to undergo further inflation, and supposedly this seems to be a process which will continue indefinitely to the future, but perhaps not to the past. Any given fluctuation, like the one that we are perhaps sitting in, has a beginning, but the overall scenario of self-reproduction need not have a beginning, although it could. And faced with this type of random and stochastic evolution, you have to take seriously the fact that observable quantities will have some probability distribution of outcomes in this picture. Nobody yet knows how to actually calculate those probability distributions because of rather awkward problems about the definition of probabilities in this infinite network. But you imagine that were it possible, you would perhaps be able to produce some probability distribution for some quality, some attribute of all these regions, like the amplitude of density perturbations or the entropy and so forth. And you would then be in the business of saying, well, we believe that life or a complexity of some sort is possible in some range. And we're not interested in the most probable outcome necessarily in this process if it doesn't allow observers to exist, but just in the narrow band of conditional probability where the value of the constant allows observers to persist and evolve. Well, let's look a little at varying constants that we will hear about from some speakers. There's a tradition in the literature that all you need to do to constrain possible variations of constants from observation is take formulae from physics where the constants don't vary and just change those constant constants into varying constants. And the whole literature is sort of covered with attempts to do that. Well, in Newtonian gravity, for example, this seems a rather simple thing to do. You can just change the gravitation constant to a time variable. But if you try to do it in general relativity, it doesn't work, because Einstein's theory is geometrical and it's constrained by the geometry on which the variations take place, and also all forms of energy, in particular the kinetic energy associated with a varying constant, will gravitate. So if in general relativity you just try to change the gravitation constant to a time variable, this is not the trace of the Einstein tensor. Yes, Halleck hasn't really come out. But if you take the divergence of this, then by a theorem of differential geometry it disappears, and the product rule applied to this combination gives you grad G here and div T here, but conservation of energy momentum means that the divergence of TAB vanishes, and so necessarily the gradient of G has to vanish. So if you want to introduce varying G, you have to work rather harder. G has got to be a function of some field, logically perhaps a scalar field, and then that scalar field must satisfy its own conservation equations, and it must contribute to gravitation. Well, the first idea of trying to introduce varying G and having a motivation for doing it came curiously from Paul Dirac. In a short paper or letter to Nature that he wrote while he was on his honeymoon, and in those days if you sent a letter to Nature it appeared 3 days later. Gamow remarked on this after reading this paper that you see what happens to people when they get married. And what Dirac pointed out, in short, was that if you look at and count roughly the number of atoms inside the horizon, so inside the visible universe, then you obtain a large number, 10 to the 78, if you use the present age of the universe, or the age in 1937, which was actually quite a bit different than just 2014 minus 1937. But I won't go into that. But you can see this is a time-dependent quantity. If you came back in 1 trillion years, you would get a different answer. There would be more particles inside the horizon. And this large number he thought was bad enough, but if you looked at the ratio of the electromagnetic to the gravitational force between two protons, then you got another number, just the ratio of two of those dimensionless quantities I showed earlier on. And this has a value of about 10 to the 39. And this just depends on fundamental constants. So Dirac proposed that this could not be a pure coincidence, that these numbers are such that this one squared is roughly equal to this one. Maybe they are really equal in this way, and that n1 squared is equal to n times some small dimensionless constant, and that there is a missing law of physics which this represents. This is a revolutionary thing to do because everything in this formula is a constant, but up here there is a time. So one of the constants in these two expressions would have to be a time variable. And Dirac, having invested considerable effort in things to do with C, MP and E, did not want to change their status in any way that might damage quantum theory. So he picked on big G and pointed out that if big G was a function of time, and in particular fell like 1 over the time, then these two formulae would both have a time dependence proportional to time squared, and that this might explain the appearance of this very large number. Well, in 1957 first, and then in a short note to Nature, Robert Dicke pointed out that this was not, in fact, just a coincidence, and that there were good astronomical reasons which would make you expect to have this sort of relationship between those two numbers, although perhaps not necessarily the actual scale of the number. And that if you estimate the main sequence hydrogen burning time scale for a star, and you say that it's rather likely that we are on the scene looking at the universe at that time, or close to it, because we wouldn't be around before the stars came on the scene, and we might not expect to be around after they all die off, then this formula turns out to be identical to this n approximately n1 squared relation. Back in 1978, I think, 79, I had a letter from Dirac, a very short letter, which commenting on something and saying that he didn't believe Dickey's argument because while he accepted that we would not be on the scene looking at the universe before the stars were born, he didn't believe that when the stars died that all life would die out. He believed that life would continue forever. Well, these sorts of approaches to describing varying G theories give you a recipe for all sorts of types of varying constant theory. So the idea is that you pick on your dimensionless constant, it might be G or GMP squared, or alpha, or a mass ratio, ME over MP, and you promote these from being purely constants into being functions of some scalar field. And all of these theories then have a particular type of structure. There'll be field equations where the energy density of the motion of this field will gravitate, but there will be a conservation equation for that field, conserving its energy and momentum. And they all have the same type of structure. The D'Alembert for the field will be proportional to some combination of the pressure and density which couple to the field. And the proportionality will be some type of new constant of nature, which is the coupling constant for the theory. And then depending on its nonlinearity or the way in which it's embedded in the gravity theory, there'll be some function of this field. So in the case of Brand-Stickey theory, the coupling to matter is rho minus 3p, and this field is just 1 over what we call Newtonian big G. In the theory for varying fine structure constant of Bekensteins and Samvik and Magueja and myself, the same type of structure prevails. The coupling in this theory is to just the particles which carry electric charge. And the fine structure constant looks like defined to be e to the 2 psi in this theory. So if the variations are small, then this field here will be typically of order 1. Here's Brand-Stickey, rather quickly, collection of field equations. Here's this conservation equation. Cosmological solutions can be found. This constant's unusual because its variation actually affects the expansion rate of the universe. And so if you have a variation in the gravitational constant as a power law, then this communicates effects into the Friedman-like power law behavior of the flat Friedman universes. But the theories all have the same type of structure. The gravitation parameter now is constant throughout most of the radiation era except at the beginning. Then it falls. Then once the universe becomes dominated by curvature, it becomes constant again. What about variations of the fine structure constant? In some ways, these are easier to deal with because for the magnitudes involved, they're not going to have any significant effect upon the expansion dynamics of the universe, reflecting the fact that electromagnetism is not going to have a global competitive effect with gravity because electric charge comes in positive and negative varieties, but mass is only positive. Laboratory measurements of variations of the fine structure constant can be looked at in terms of the sensitivity that you would have with an atomic clock, now less than a few times 10 to the minus 17 per year. It's the accuracy a few years ago. It's interesting to compare that accuracy of a second over 1 or 2 billion years, with the accuracy of Harrison's H4 clock in 1716. So Harrison was 300 billion times weaker. However, in some ways Harrison is the more impressive technological achievement. Harrison was accurate to 39 seconds over 47 days, tossing around at sea in corrosive, salty conditions, and so on, with mechanisms that never needed maintaining. But cosmologists realized that one could do rather better than these laboratory experiments by exploiting the huge age of the universe. So, for example, if you could look at the light from distant quasars at high redshift and find a way to compare the spectra in a definitive way with the spectra that you measure on Earth for the same species, you could compare whether physics and the constants were the same nearly 10 billion years ago to what they are today. Well, if one develops a theory like Brand-Sticky for varying alpha, it has a very similar structure in its solutions to Brand-Sticky theory. That is, during the radiation era, the fine structure constant will be essentially constant. But once you become dominated by cold dark matter or some other pressureless form of matter, alpha starts to change, but very slowly, just logarithmically in time. If the universe were ever to become dominated by curvature or dark energy, the variations are turned off because the expansion rate becomes too quick. So this is your scenario. So even though alpha has a latitude to vary really quite extravagantly, the variations are really quite small and over just this finite looking period. Well, John Webb is going to tell us later about how one uses quasar spectroscopy to get information about the possible variation of the fine structure constant. The sensitivity here from the time when we began this work at the end of the 1990s was much greater than was possible in any laboratory experiment. That was the great novelty of it. And the new technique that led to that was to focus upon the relativistic fine structure in the quasar spectra. So here is an exaggerated simulation. If one looks at wavelengths of various species and you were to shift the fine structure constant by these large factors here, just to exaggerate the effects, what you can see is that due to the competition between two relativistic terms for the energy or the wavelength of these species, in some cases you get a very significant shift in the value of the rest wavelength as you change alpha. But for other species, these sort of anchor-like species, you don't get any perceptible shift. And also in some situations the shift goes in the opposite sense to what you see here. So comparing the shift in the separation between two species is a rather interesting thing to focus on. You couldn't on the back of an envelope predict whether there would be any shift, let alone what the sign of the shift would be, without doing these sorts of detailed many-body calculations that Victor Flambaum and co. at New South Wales have done. So you'll hear a lot more about that from John Webb. Last few slides, what sort of outrageously speculative and peculiar things could one do with constants? There are people like the late Ted Harrison who used to worry about whether constants could be manipulated in the same way that people wonder about whether you could create universes in the laboratory or initiate inflation at some local point in the universe. And then there are people who have wondered whether the values of the constants of nature evolve in the collapse and re-expansion of black holes or collapsing universes. Here's two simple examples. Okay, Tolman famously produced this prediction that if you had a closed universe that had entropy increase, then you might expect the maxima of expansion to increase. What he didn't do was to include a positive cosmological constant. And if you do, these oscillations necessarily cease. There comes a time when the cycles get so large that the cosmological constant comes into play. And when it does, there's no further bounce and you head off to de sitter. Interestingly, the last bounce is therefore always going to be in a situation where the relative energy densities in the cosmological constant and in the matter fields in the model are always roughly the same. In fact, with the cosmological constant energy being just slightly bigger. Not dissimilar to the situation that we see. But of course, there is no reason to predict that it would happen at a particular scale. The other interesting thing about varying constant scenarios with a cosmological constant is that the presence of a cosmological constant stops the variation at late time of constants like the fine structure constant. And if you didn't have a cosmological constant, then alpha would just keep on steadily increasing forever, and eventually there wouldn't be any stars and there wouldn't be any atoms, and there wouldn't be any complexity in the universe. So the cosmological constant plays a rather curious role here. It turns off the variations of these scalar fields of the sort that drive varying constants. So there's actually an anthropic type of lower bound on the cosmological constant as well as an upper bound. If you have an oscillating universe with the possibility of varying constants like alpha and g, so the Tolman problem with entropy increase, then the situation is rather interesting. Here's the varying amplitude of the scale factor Tolman found. What happens to variations, say, of alpha in such a theory? Well, alpha doesn't oscillate. Okay, it's not allowed to oscillate. You can see from the conservation equations very easily. It's allowed to have a minimum or a maximum, but it cannot have both. And therefore, alpha, and in fact g, if you do the same thing with g, just continues essentially monotonically with rather sharp changes at the bounce forever from cycle to cycle. So the constants don't oscillate, they just vary monotonically. Lastly, this idea of some type of natural selection of constants that has been proposed in the past, the idea being that perhaps new universes form in the collapse of black holes or whole universes, and when they bounce, following John Wheeler's sort of dream, maybe the constants are reshuffled and become different in the new cycle, so that they don't just vary monotonically as they do in all the theories we've looked at. And Smolin's speculation was that therefore you might expect that universes that produce lots of black holes will therefore proliferate over a long period of time, and we would expect therefore in our universe that if we look at the values of constants, if we perturb them slightly in our minds, then we might expect the black hole production to go down. That is, that we are at a local maximum for black hole production. The problem with this is assuming that changes in the constants, as it were, define these little turning points for the production of universes. A better way to look at it is to write down the entropy of the black hole, which depends on g, say, and the mass squared. And you can see, as in Smolin's scenario, entropy increase will be brought about by increasing the mass of black holes, having more and more and more black holes. But there are some constants, clearly like g, which don't inhabit little local maxima. So they are just slopes, as it were, and you could increase the entropy of the situation not just by increasing the mass in black holes, but by increasing g from cycle to cycle without limit. So there is not a sort of turning point, there's not a local maxima for shifts in g. So the scenario would just run away with entropy increase with increasing g from cycle to cycle of the collapse. Okay, that's all I really have time to say for now. I hope I've given you some sort of random walk through some of the topics that make constants of nature interesting and why cosmology has something to say about them. There's very little in this particular meeting about anthropic principle or fine-tuning, because the last Oxford meeting was devoted to that topic, and you can see it filmed on their website. So if you have any questions, I will be happy to to try and answer them, but ideally you should address all your questions to the speakers to come.